Hello everyone. In this lecture, you will see we will see a nice result regarding uh, finite subgroups of the group of all upper triangular invertible matrices over rational numbers. So let's start with uh, what the invertible matrices are, and after that we will see how to show that any two finite subgroups of the invertible matrices over rational numbers are conjugate. Okay, so let's start with, so here GLN. So for any field F, we denote GLN of F as all those matrices in all those m cross n by n matrices inside F and F such that determinant of A is non-zero. Okay, so we all know that it forms a group under a multiplication. So GLN F forms a group under multiplication, and those of you who are familiar with some algebraic geometry and algebraic groups, you know that this GLN is an algebraic group, or in fact it is a connected reductive algebraic group. So we are not going into that direction. We are simply prove our result. Okay, so this under matrix multiplication. Okay, matrix multiplication. Okay, so here it is our main result. So our main result is the following, that any two finite subgroups of GLN Q, where Q is the set of all rational numbers. So any two finite subgroups of GLN Q are, or so let me state in this way, that any finite subgroup of GLN Q is conjugate to some subgroup of GLNZ. So first, okay, so to prove this result, we will need some definitions regarding lattices and all that. So let me start with the definition of the lattices. So lattice in Q. So it is basically so lattice in Qn, where lattice in Qn. So so here Qn means that Q, it is the uh, Cartesian product of all Q in times. So lattices inside Qn is so is defined in the following way. So you choose so suppose choose a basis v1 vn of Qn over Q. Now take the linear span z v1 direction z v2 direction z vn. Then this forms a lattice in Qn. Okay. Now if you choose if I choose if I choose in particular the standard basis of Qn over Q. So if we choose the standard basis E1 En of Qn, where Ei is nothing but 0 0 0 1 0, all entries are 0 except the ith entry. So this forms a basis of Qn over Q. Then ZE1 direction ZEN, which we denote this as Zn, that is the sum of the direction of the copies of Zn. This is called the standard, it's called the standard lattice in Qn. Okay. And okay, yeah, and also we need the definition of G ln Z. So let me start with the definition of G ln Z. So if R is a commutative ring with unity, then Z ln R is defined as all those A inside M and R. It is the n-cross-n matrix with coefficients in R, such that determinant of A is a unit, is a unit in R. Okay, unit in R. So if you take, so in particular, if R is equal to Z, so if R is equal to Z, so it is a commutative ring with the unity 1, right? So G ln Z is nothing but all those a inside m and z such that no, determinant of a is a unit in z. But we all know that the units in z are precisely +1 and -1. So that means that z ln z is all those a inside m and z such that determinant of a is equal to ±1. Okay. Okay. So and also you can check that also you can check that if x is equal to the set of all, if x is equal to the set of all lattices in Qn, then G ln Q acts on the set X transitively. So if X is equal to the set of all lattices inside Qn, then the group GLN Q acts on the set X transitively, right? So I think we don't need this result. So let us see the proof whether we can do. Yeah, actually we need this result. So those of you who don't know about the group action, see some standard book on group action, and then you can see what is the group action, what is the transitive action on all that, and what do you mean by that a group acts on a set transitively, and the stabilizers in all these things. So reference for this is any standard book on algebra. So just look for the orbit, stabilizer, transitive action, and orbit stabilizer theorem. Okay. Now we are going to prove our main result using all this machinery. So the theorem is that any finite subgroup of G ln Q is conjugate to a subgroup of G ln Z. Okay. So the proof is easy using all this machinery. So proof, let us start with the proof. Now just X, so let X be the set of all lattices in Qn then gln q acts on X transitively okay. Now consider the standard lattice in Qn, the standard lattice in Qn. So denoted by L naught, denoted by Zn, right? Yeah. Now, so okay. So now take let A be any finite subgroup of gln q. Suppose A be any finite subgroup of gln q. So we have to show that A is conjugate to a subgroup of z ln z, right? So then just okay. So now consider the lattice L. So how it is defined? L is nothing but all those translates of these lattices A inside A. So this L is again forms a lattice, and since z ln q acts on X transitively, so the stabilizers of any two lattices inside z ln q are conjugate, right? So it is a standard result in the group action. So thus a stabilizer of L inside gln q is conjugate to some is conjugate to the stabilizer of G of L naught. So it is nothing but X stabilizer of L naught in G ln q X inverse for some X inside G ln q. Okay. Now if you notice that, but if you notice that stabilizer of L naught in G ln q is nothing but G ln z. Just it is nothing but G ln z. So and also that A, this the finite subgroup A is contained inside the stabilizer of L in GL and Q. Okay, so now which is equal to X GL and Z X inverse, right? Now take H equal to X inverse AX. So it is contained in GL and Z. Okay, so it is contained. Then our A is equal to XH X inverse, right? Where H is a subgroup of GL and Z. Okay, so we have proved that any finite subgroup of G ln Q is is conjugate to a subgroup of Z ln Z. So in fact we have a more precise result. So let me end this video with the with a question that that consider the set. Suppose F is a field. Suppose F is a field. Consider the set sigma is equal to the cardinality of A, where A is a finite subgroup of G ln F. So when a set of real numbers are given, so the natural question is that whether sigma is bounded or not, right? So the natural question arises whether sigma is bounded or not. So over real numbers or complex numbers, so when F is equal to R or C complex numbers, the answer is negative. The answer is no. The answer is no, because for any integer, for any positive integer d, for any positive integer d, look at the matrix x is equal to, look at this matrix, 2 pi by d minus sine 2 pi by d, sine 2 pi by d, cos 2 pi by d. Then order of x is equal to 1. Sorry, order of x is equal to d. So if we consider the cyclic group generated by x, so this has order d. So for every positive integer d, we have a finite subgroup of GL to R or GL to C. So in fact that there is no upper bound for the cardinality of the finite subgroups of GL to R or GL to C. But for F is equal to R, sorry, for F is equal to Q over the rational numbers, the answer is affirmative. The answer is affirmative. So in fact we have an upper bound for sigma over when F is that is sigma has an upper bound depending on n. So the n we choose, okay, depending on n. So so it is proved by it is proved by uh, Min, it is proved by Minkowski in 1887, around 1887. So in the next video you will see the proof, the idea of the proof, uh, uh, so that uh, we can get an upper bound, a precise upper bound for the cardinality of the finite subgroups of GLM over Q. Okay, so let me finish with this.